Cadaverin has an extremely pungent odor and it is very difficult to wash off. Even contact with just the vapors will cause materials to stink. Working with gloves and proper safety gear is an absolute must, and this must be only carried out in a well-ventilated area. Cadaverin gets its name from the root word cadaver and is naturally produced in the decomposition of animal tissue. It is a major contributor to the putrid smell of rotting meat. One interesting fact is that human semen actually contains a small amount of cadaverin, which contributes to its own distinctive smell. For this experiment, the amount of chemicals that you use will depend entirely on how much cadaverin you want to make. Also, the amount of chemicals that I used was somewhat arbitrary. During the reaction, lysine hydrochloride will break down to release hydrogen chloride gas. The sodium bicarbonate is included to neutralize the HCl gas. I provided the amounts of each chemical just to show the proportions that I used them in. The use of ethanol or water is optional if you want to extract your cadaverin after you've made it. Most of the starting products and the byproducts are not soluble in ethanol. So ethanol is a good choice if you want to extract the cadaverin and then concentrate it. Because this isn't being used as a reagent, you could also simply use water just to dissolve everything. In this video, I'll be using two basic methods. The first is just a basic heating of the lysine, and the second is an example of destructive distillation. First, 0.5 grams of lysine hydrochloride was added to a small 10 milliliter round bottom flask. Next, a very generous amount of 0.25 grams of sodium bicarbonate was added. The flask was then shaken vigorously to mix the two powders as well as possible. The sodium bicarbonate is added to neutralize the hydrochloric acid that is liberated when the lysine hydrochloride is heated. Next, the mixture is heated using a Bunsen burner. You need to move the heat around a lot and be careful not to burn any of the lysine. However, unfortunately, burning the lysine can happen very easily. After heating the lysine slightly, you'll notice that the powder starts to turn a dark brown-yellow color. The yellow color is the cadaverin oil that is forming. Cadaverin is formed from lysine by a decarboxylation reaction. Lysine is an amino acid, and like all amino acids, contains an amine group and a carboxylic acid group. These two groups logically give the name amino acid. In a decarboxylation reaction, heat is applied and the carboxylic acid group, as shown in red, will break off the molecule and leave as carbon dioxide gas. When the carboxylic acid group leaves, it is replaced with a single hydrogen atom. Because the decarboxylation reaction results in the loss of one carbon atom, this reaction can be used to shorten a carbon chain. Once the carboxylic acid group is kicked off, we are left with a very simple diamine called cadaverin. While the lysine is a white powder, the cadaverin is an oil. I then rotated the round bottom flask so that I could heat the other side. Unfortunately, when using this method, a lot of the powder will remain unreacted. After a while, when it looked like the amount of brown liquid forming had slowed down and almost stopped, I removed the flask from heat. You can test to see if you got cadaverin by smelling it. Cadaverin is described by many as having the smell of strong semen, and in this concentration, the smell should be quite powerful. After letting the flask cool for a bit, I added 10 milliliters of anhydrous ethanol. 10 milliliters was likely overkill, and you could probably get away with much less, around 3 milliliters or something. I added a mini stir bar and I let the ethanol stir for about 20 minutes. I then let the solution sit for about 30 minutes so that the particulate could settle to the bottom. I used ethanol because cadaverin is significantly more soluble in ethanol than lysine or sodium bicarbonate. I then transferred the solution to a small dram vial, and unfortunately you can see that the solution still contains quite a bit of particulate. Then, under a small light jet stream of air, I evaporated the ethanol. The white particulate in the solution is mainly sodium bicarbonate, salt, and lysine. As the solution evaporated, it looked like the particulate was going to be a problem and build up at the bottom, but once the vial was dry, you can see that there was very, very little amount of particulate that was actually present. In the end, I'm left with a dram vial with a very small amount of solid particulate at the bottom, but with a lot of yellow viscous oil on the sides and on the bottom as well. The oily liquid on the side is the cadaverin. You can redissolve it in a small amount of ethanol or water and have yourself a nice cadaverin extract. Next is the destructive distillation method, which is a much more efficient process. This is an improvised destructive distillation setup that I made. For this run, I used 1.3 grams of lysine and about 1 gram of sodium bicarbonate. Inside the tube is filled with nitrogen gas. There's absolutely no oxygen. Because there's no oxygen, nothing inside the tube can combust. This means that even if I apply a lot of heat, the product cannot burn. Out of the stopper is actually a passer pipette tube that I bent to 90-degree angle using a Bunsen burner. This leads into a small dram vial containing some water. The idea here is that the lysine can be heated to high temperatures to decarboxylate as much of it as possible. However, since Kadaverin boils at 179 degrees Celsius, a lot of it is going to be vaporized. The Kadaverin in its vapor form will lead out of the tube and then bubble through the water and be trapped. It is important to use water here in the trap instead of ethanol because we are working with a flame. The water seemed a little bit low, so a bit more was added to the dram vial. As I heat up the test tube, you'll see a lot of brown yellow liquid condensing on the walls. This is the Kadaverin that is vaporizing and then recondensing. Near the end of the distillation, you'll notice that some of the water is getting sucked up out of the dram vial and into the tube. This is because as the gases in the tube were heated, they expanded and were expelled out of the tube. When the heat is removed from the boiling tube, the gases cool down and contract and create a negative pressure and pull some of the water out of the dram vial. If the flame from the Bunsen burner were completely removed from the boiling tube, suckback will occur. The pressure in the tube will decrease enough that all of the water in the dram vial will be sucked back up into the boiling tube. In almost every case of destructive distillation, this is completely undesirable. The easiest way to avoid suckback is to remove the dram vial before you remove the heating. This way, the suckback will occur, but it will only pull in air and not your water solution. In this case, I let the suckback occur because a lot of the Kadaverin was still in the boiling tube and I wanted to handle the solution as little as possible. It is highly advised, however, that if you choose to do this, you do not let the suckback occur because it can be dangerous. Depending on how hot the test tube is, it can rupture when the cold water hits it. Luckily for me, everything worked out fine. Occasionally you can see some oily Kadaverin sludge moving through the bent passer pipette tube into the dram vial. In theory, you can include no water in the dram vial and simply just collect the distilled over Kadaverin. However, I opted to use water because I want to limit the amount of Kadaverin vapor that entered into the lab air. Unfortunately, I didn't catch the suckback on film, but this is what it looks like after it pulled all of the liquid out of the dram vial. This is what the water Kadaverin solution looks like at the bottom of the test tube. I transferred the solution to the small dram vial and immediately capped it. A 100% yield would give about 1 milliliter of Kadaverin. However, I'm estimating that we have at most here about a 40% yield. The odor of the Kadaverin solution in the dram vial was nonetheless quite horrible. If you wish, you can concentrate the Kadaverin using diethyl ether to extract it. However, I chose not to proceed any further.